Good morning everyone, welcome to today's GCSE Chemistry live group tutorial. The topic today is the transition metals. Hope you all had a nice evening. Today is the first of 4 of our live group tutorials. So this is chemistry, then we've got English at 11, maths at 12:15 and physics at 2 p.m. So this will be a 1-hour session, so it will end at 11:15. And the session will be led by our usual brilliant chemistry tutor, Aman, who has been with us for a really long time, is a very experienced tutor, and lots of you have had sessions with her before. Aman studies medicine at King's and has done over 150 lessons with my tutor. So as usual, just pop any questions you might have for Aman or for myself in the chat or the Q&A, and we'll do our best to keep an eye on those throughout the session, and then we'll have some time at the end as a dedicated Q&A time to answer any of those questions that we may have missed throughout. And the first part of the session will be content from Aman. So just wait a couple of moments for a few more people to join us. As usual, this lesson will be recorded, so you can watch it back if you miss anything or would like to take more notes. And all of our live group tutorials are available to watch on the My Tutor YouTube channel, as well as some extra shorter topic videos that are related to all the topics that our tutors are going through that might be handy for you to have a look through. So yeah, someone's just asked, where do you watch it back? So if you just go onto YouTube, type in My Tutor, we have a channel and all the videos are there, and they're separated into different subjects. So it should be quite easy to find what you're looking for. Cool, Aman, are you all ready to go?
Yep, that's fine, we can start.
Brilliant.
So welcome back everyone. So this is the last tutorial on the periodic table today, and we're going to be looking at the transition elements, specifically, so that's the block in the middle. I'm going to show you on the periodic table now. So it's between groups 2 and 3, so here and here, so this big block in the middle. We're going to be looking at that, and then we will go on to the history of the periodic table very briefly, and hopefully a summary of everything we've covered this week. And then we'll do some exam questions. So the transition elements, as I said, they're this big block in the middle. Remember yesterday we looked at the alkali metals, which were group 1, and group 7, the halogens, and on Wednesday we looked at the noble gases in group 0 or group 8. So the properties of transition metals, before I go into these, I think it's important that I mention all the different exam boards. So with regards to the AQA exam board, what you need to know is the differences between the transition metals and the alkali metals. So the properties that the transition metals have compared to the alkali metals, which we will go through today. The Edexcel exam board adds to this slightly. They want you to know the differences, but they also want you to know some of the uses of the metals, as well as that they want you to know about alloys. We covered alloys a couple of weeks ago, so you can have a look about on alloys if you're in the Edexcel exam board through that tutorial on YouTube. As well as that, we need to know a few of the reactions. So all the exam boards want you to know a few of the reactions that transition metals take part in, but it's slightly different to the alkali metals, whereas in the alkali metals, you need to know how to write those equations. For the transition metals, they would tell you what equation it is, because we can't just learn all the equations that go on, whereas in the alkali metals we can, because there's only 6 or 7 of them. So let's have a look at these properties. So first of all, they are excellent conductors of thermal energy and electricity. And the reason for this is that basically because they form normal metallic structures. So you'll remember last week we went through giant metallic structures, and that's what metals form when they bond together. And all the transition metals are giant metallic structures, so they will have all the properties that you would expect of a metal. Remember, the alkali metals don't have those usual properties. So the alkali metals do conduct electricity, so that is one common thing that they both have. But the alkali metals are soft. So do you remember yesterday we covered that the alkali metals were soft? And does anyone remember why the alkali metals are soft? Someone's asking, are these transition metals? Yes, they are. So does anyone remember why the transition metals are, the alkali metals are soft? Excellent. There's basically we've got forces, the electrostatic attractive forces between the outer electrons, or the delocalized electrons, and the cations. And because there's only one delocalized electron per cation, there's quite weak electrostatic attractive force there. So the alkali metals are soft. whereas the transition metals are hard and strong. And the reason for that is that often they give more than one electron into their electron structures or into the metallic structures. So if we have a look at our periodic table, and let's try and draw scandium, which is one of the first transition metals there. It's got an atomic number of 21. So if we have a look at the electron shell of scandium then, we know the first one will have 2. Remember, that's the maximum capacity. The second shell will have 8. Again, the maximum capacity. The third shell will also have 8, which is again the maximum capacity. And then we go into the fourth and outer shell. So if we have a look, we've done 2 in the first, 8 in the second, that makes 10, and 8 in the third, which makes 18. It's got an atomic number of 21, which means there are 3 electrons in its outer shell. So what that means is that when we draw the metallic structure of scandium, it will, each ion or each scandium atom will give 3 electrons into the delocalized electron C. So if I draw that, these are our atoms of scandium, which are going to become ions, because remember, they lose their 3 outer electrons. So per positive ion, there will be 3 delocalized electrons. Like that. And so that means there's strong electrostatic attractive forces between the electrons and the protons in the nucleus of these cations. So that means that they are hard and strong, as well as that there are high melting and boiling points, because a lot of energy is needed to overcome those forces. So if we go back, so we've talked about how they're excellent conductors of thermal energy and electricity, and remember that's because of the delocalized electrons. So the delocalized electrons are able to move, so they can carry a charge. It's really important, by the way, in exam questions that you say that the electrons can carry a charge. We say that they're hard and strong because of that strong electrostatic attractive force between the delocalized electrons and the cations. And they've got high melting points, except Mercury. So we covered Mercury yesterday, but basically Mercury is one of the anomalies of the transition metals. It is a liquid at room temperature. And that is because, if you want to know, its outer shell electrons don't want to be lost. So if we have a look at the periodic table, Mercury doesn't like to lose its outer electrons. And so what that means is, instead of the electrons going into the metallic structure, they stay in the element. So there are no electrons in that C. So there's no electrostatic attractive forces between the cations and the electrons. So Mercury forms very weak bonds with each of the atoms of Mercury, and it doesn't like to lose its electrons. If you want to know a more specific explanation for that, you can study chemistry at A-level, where we look at the electron shells in more detail. The final property is that they are quite unreactive. So hopefully, if you were here yesterday, you remember that the alkali metals are really, really reactive. So they've only got 1 electron that they need to lose. We talked about, as we go down the group in alkali metals, you get further and further away from the nucleus, or the outer shell gets further away from the nucleus. And so that means that outer electron has less pull to the nucleus, because the protons in the nucleus are positively charged and they pull that outer electron in. But if we're further from that nucleus, there's less pull. So that means that that electron is more readily lost. As well as that, there is more shielding. And remember, shielding comes from the electron shells in between the nucleus and the outer shell. So as we go down the group 1 elements, as the atoms get bigger, there are more electron shells in between the nucleus and the outer shell, which means that there's more shielding, which is effectively blocking that electrostatic attraction from the protons and the electrons. But in the transition metals, this doesn't occur. They're actually quite unreactive, and that's the GCSE answer for that is that because there's quite a lot of electrons in its outer shell, it's harder for it to lose those electrons. It's not just 1, there's quite a few there. So more energy is required. And that's why with a lot of reactions with transition metals, we have to put in a lot of energy. So a lot of heat usually goes in, or we have to take a long time to react them because they're so unreactive. So let's go into some of the reactions that do take place. So most transition metals will react with oxygen. You'll remember we talked about reactions with oxygen yesterday. So we talked about things like sodium reacting with oxygen to produce sodium oxide, potassium reacting with oxygen to form potassium oxide. It's exactly the same with the transition metals. Most of them will react with oxygen. You don't need to know the exceptions, but out of interest, if you did, these are the 4 exceptions. Palladium, platinum, silver, and gold will not react with oxygen. So the only ones that all the others will. And it's just a nice equation of the metal reacting with oxygen and producing copper oxide. The hardest part in an exam question, if they asked you about a transition metal reacting with oxygen, would be producing the chemical formula of the product. So if we imagine we've got aluminium reacting with oxygen, we need to know what the chemical formula of aluminium oxide is. That's the hardest part, being able to form that. Someone's asking, what does the G mean? G means that it's a gas. So remember, oxygen goes around as a gas. These are the state symbols. So copper is a solid, it's a metal. Oxygen is a gas, and it produces a solid of copper oxide. So aluminium is a metal, so that would be a solid. Oxygen is a gas, and we're going to form aluminium oxide. So hopefully you remember yesterday we talked about how to form chemical formulas. So how do you know what charge transition metals have? That's a really good question. So often we don't know what charge the transition metals have. And what's really important is that they will tell you in the exam. So they will say, for example, copper 2 or copper 3. So remember, the transition metals tend to form different ions. So we can have iron and iron 2, or we can have iron 3. And that is telling you what charge it forms. So that would be iron 2+. Remember that metals always lose electrons. They're always going to be positively charged. And this would be Fe3+. They would never not tell you in the exam. Yes, someone's asking me, are transition metals always a positive charge? Yes, they are. Always, because they're still metals. So remember, metals always lose electrons, whereas non-metals always gain electrons. So if we go to aluminium, aluminium plus oxygen forms aluminium oxide. This is just an example of how to draw or come up with a chemical formula. So aluminium is in group 3, so it's not a transition metal, but I just want to show you how to form a chemical formula. So if we know it's in group 3, that means it has 3 electrons in its outer shell. So if it forms an ion, it forms Al3+. Oxygen is in group 6. And if it's in group 6, that means it has 6 electrons in its outer shell. Remember, oxygen is a non-metal, so that means it wants to gain electrons. If it gains those electrons, it will gain 2, and therefore will form an O2- charge. Because it will gain 2 electrons, it will have 2 more electrons than protons. So now if we want to combine these two, that means that we would need to have 2 aluminiums for every 3 oxygens. And that is because each oxygen wants 2 electrons and each aluminium has 3 to give. So in order for aluminium to use up all of those 3 and oxygen to gain them, for them to combine, we would need 2 aluminiums, which would give 6 electrons, and oxygen would need 6 electrons. So that's the way they combine. And I've told you before, if this confuses you, you can just swap the charges. So if you have a look, Al3O2 just swaps to Al2O3. So the 2 from here has come down here, the 3 from there has come down there. So if it confuses you, you can just swap the charges. Okay, so that's how to form that, and that's what would probably be the hardest thing in the exam, just forming that chemical formula, which is a higher tier thing to do. The next reaction is that some transition metals react with water and oxygen. You may remember that if the reaction of water and oxygen is called rusting, and there's only one transition metal that will do it, and that's iron, but there's one alloy. Does anyone know the alloy of iron that also rusts? Steel, excellent. So steel is the alloy of iron that also rusts. So iron and steel will rust, and that is when they react with water and oxygen. And what's really important is that you need both water and oxygen there for rusting to occur. Now I'm going to swap over to the Edexcel exam board now. So all the exam boards require you to know about rusting, but Edexcel want you to know how you can prevent rusting. So to prevent rusting, what we can do is we can either remove the water or we remove the oxygen. So in order to remove the water, we can use something called a desiccant. Does anyone know what a desiccant is? And it's okay if not. No? Okay, so a desiccant is something that absorbs water vapor. So there's lots of different compounds that absorb water vapor. One of them is calcium chloride. Silica also does it. So remember, silica is silicon dioxide. So it tends to absorb water. So that's the meaning of desiccant, and it absorbs water vapor. So if we put iron with a desiccant, such as calcium chloride, it will absorb all the water vapor in the air, so the iron can't react with water. So that's what we can use to remove water. To remove oxygen, If you think back to Wednesday, we covered the noble gases. And remember, the noble gases are unreactive, and a lot of them have a higher density than air. So that means if we put iron with something like argon, it will stop the air reaching the iron, and it won't itself react with iron. So just to explain that again, if we put the iron with argon, argon is more dense than air, which means it stops oxygen in the air reaching that iron. And as well as that, we know that argon is non-reactive. Remember, the halogens, sorry, not the halogens, the noble gases all have a full outer shell of electrons. And because they have a full outer shell of electrons, that means they don't react. So the argon won't react with the iron. Someone's asking me, what does desiccant mean? Desiccant means that it absorbs water vapor. Well done. The person that's saying sacrificial metal, that is another way to stop iron reacting with water and oxygen. So the two ways that I've described are removing water and oxygen. There are other ways, such as painting the iron. As well as that, you can use something called galvanization, which is using a more reactive metal and coating it with the iron. So for example, zinc is more reactive than iron. And you'll cover this when you come onto the reactivity series, which we're not doing today, but you can use the reactivity series to help you with this. But zinc is more reactive than iron. And so if we coat iron with zinc, that will stop the iron reacting with water and oxygen. And that is called sacrificial protection. So the zinc is sacrificing itself. Another metal that will do that is magnesium. And the other thing that you need to know about this is that it forms hydrated iron oxide. So all the exam boards want you to know that rust is hydrated iron oxide. I apologize that that's quite difficult to see. So it's hydrated iron oxide. Okay. Halogens are group 7 elements. So the person that's asking me that, they are group 7. If you want to know about the halogens, we covered those yesterday. Okay, then the other one is some transition metals react with halogens. So halogens, as I said, we covered them yesterday, things like chlorine, bromine, iodine. So some of them will react. So for example, we'll do the reaction of zinc with iodine. So zinc plus iodine will go to zinc oxide, sorry, zinc iodide. So again, it's quite a simple reaction. You just react the two reactants together and form one product. Am I now doing AQA? So all these reactions need to be known by AQA and Edexcel. The addition for Edexcel was knowing how to stop rusting. So this is all the exam boards need to know about the reactions, but Edexcel want you specifically to know about how to prevent rusting. So this reaction, zinc plus iodine goes to zinc iodide, you need to know, all the exam boards want. So if they give you a question in an exam about a transition metal, they will tell you which transition metal and they will tell you which halogen. You wouldn't be expected to know which transition metals react with which halogens, they would tell you. Okay, someone asked me, why does mercury have a low melting point? And as I said, the official answer you will learn at A level, and it's to do with the electron shells. I'm not going to be talking about it today because it will confuse your GCSE knowledge of electron shells, because from GCSE to A level, you learn more about how electron shells work and it gets a little bit more complicated. But the GCSE answer for that is that mercury doesn't like to lose its outer electrons. So most metals will lose their outer electrons, but mercury has kind of an extra force in its nucleus that pulls those electrons to the protons in the nucleus, which means that mercury doesn't like to lose its outer electrons. And that means when it forms its giant metallic structure, it doesn't tend to have delocalized electrons in the sea of electrons. And so there's no electrostatic attraction between the delocalized electrons and the cations, which means that it has a weak or low melting point because of those weak electrostatic attractive forces. Okay, so we've covered the properties of transition metals and we've covered the three reactions that we need to know. So remember, they react with oxygen to produce an oxide. And we've talked about transition metals reacting with water and oxygen. So remember, that's iron and steel that will do that. And we've talked about some of the transition metals reacting with halogens. And again, you will have two reactants and a product. And remember, you need to be able to balance equations. If you want to know how to balance equations, we covered that on Tuesday. Okay, so someone is asking me, what does high and low boiling points mean? And how do we know which metals have what type of melting and boiling point? That's a really good question. So boiling points refer to when a liquid becomes a gas. A melting point refers to when a solid becomes a liquid. A high melting point or high boiling point means that a lot of energy is needed to overcome some bonds. So for example, most metals form strong bonds or strong electrostatic attractive forces between the electrons and the cations, which means a lot of energy is needed to overcome those bonds and therefore break that structure up to melt a metal. So that would be a high melting point, and a boiling point would be if we're converting a liquid to a gas. Low melting and boiling points are things like the alkali metals, which we covered yesterday. So the alkali metals don't have very strong electrostatic attractive forces between the delocalized electrons and the cations, and that's because there's only one delocalized electron per cation. So there's weak forces there, which means not a lot of energy is needed to overcome those forces, so they have low melting points. Another example would be in covalently bonded structures. So remember things like oxygen. Oxygen is covalently bonded and it forms a pair, but oxygen molecules, even though they go around as pairs, remember there's weak intermolecular forces between the pairs of oxygen. So what that means is that when you try and boil oxygen, so remember oxygen at room temperature is a gas, that means it has a low boiling point. And the reason for that is because there's weak intermolecular forces between the molecules of oxygen. So hopefully that explains what melting and boiling points are. What's a cation? Really good question. So a cation is a positive ion. So remember, an ion just means a charged atom. So if, for example, we take aluminium, aluminium has 3 electrons in its outer shell. If it loses those 3 electrons, there will be more protons than electrons. So it forms an aluminium 3+ ion. An ion just means it's charged. It's charged now because there are more protons than electrons. Remember, in an atom, the protons and electrons should be equal. But if you get more of one than the other, then it becomes charged and becomes an ion. Okay, so let's now go on to the formation of coloured compounds. So all the exam boards require you to know that transition metals form coloured compounds. You don't need to know why. Again, if you want to know, you'll learn at A level, but it is to do with what type of light they give out and the wavelength that the transition metals have. And it's also to do with their electron shells. So the colours that you need to know are on the board. Basically, all the exam boards want you to know about the main transition metals. So that's manganese, cobalt, copper, iron, chromium and nickel. These 3 are added in for interest, but the others are all there that you need to know, and I've done them in the colours that they form. So manganese forms a pink iron, coloured solution, sorry. Cobalt also forms kind of a pink, copper is blue, iron 3 is brown, iron 2 is green, nickel 2 is green, and chromium 3 is green. If you want to know, permanganate forms a purple iron, dichromate forms an orange iron, and chromate forms a yellow iron. What are coloured compounds? Do they come when 2 transition metals bond together? So yes, so most of the transition metals are coloured. What would be really good is if you have a look on the internet after this session, you have a look at some of those ions. So for example, copper chloride, things like that, you'll find that they have coloured compounds. So copper chloride will be blue, something with iron in it would be brown. If it's Fe3+, if it's Fe2+, it will be green. So the compounds, so if they bond with something else, it's not necessarily with each other, it's with something else usually, they will form a coloured compound. Okay. This is now an Edexcel topic, so the uses of transition metals, but for the other exam boards, sometimes they do ask you what you think the transition metals could be used for, so it's quite universal. So the first one we'll think about is aluminium. Aluminium can be used as a foil, so you may think that we use this kind of when we're cooking, and the reason we use it is that it does not react with water. And that's because of the oxide layer. So remember I talked about how most of the transition metals will react with oxygen to form a metal oxide. So it does not react with water because that oxide layer protects it. As well as that, it's malleable. So if you think about foil, foil is quite bendy, you can scrunch it up and you know that it moves quite easily, and it's very light, and that comes down to the low density. So these are the properties of aluminium that means it can be used as a foil. If we think about copper, copper is a really good electrical conductor, which means that it's used in electrical wiring. And as well as that, it resists corrosion. So that means that if we use it in wiring, it won't react with water in the air or anything that's in the air, that will then allow it to corrode. So it's really good for electrical wiring. And the final example is gold. So gold is used in jewelry. The reason it's used in jewelry is because it is very unreactive. So you remember I covered which metals react with oxygen. Gold was one of the metals that does not react with oxygen. Malleable means that it can be basically hammered into different shapes. So ductile means that a metal can be drawn into wires. Malleable means that it can be kind of changed into different shapes. So remember, aluminium, you can move it around, you can make it into a different shape, but it's not going to break up that metal. Gold, as I said, is unreactive. It's one of the transition metals that does not react with oxygen. It stays shiny, and that's because it's unreactive. Also, it's soft and it's malleable. Again, gold can be moved into different shapes. So that's why it's used in jewelry. So they're the three main metals that we need to know about. So before we move on, does anyone have any questions about transition metals? I'm going to move on to the history of the periodic table very briefly. No? Okay. All right, so we'll start off with the history of the periodic table. Someone's asking me about equations. We will do some questions at the end, which will have equations in them. Okay, let's look at the history of the periodic table. So it started off with John Dalton in 1808, and he produced a list, which looks a bit like this. And that list basically ordered the elements, or the elements that had been found at that period of time in terms of their atomic weights. So if we have a look, hydrogen weighed 1, I think that was argon, it weighed 5, carbon weighed 5, oxygen weighed 7. So they were going in atomic weights as a list. And this was the first guy that produced the periodic table. Do we need to know the dates? No, you just need to know the 3 different periodic tables that were produced. So I'm going to go through all 3 of them. This is John Dalton's. This was the first one. It was a list in order of atomic weights. And this was all the ones that had been produced then. You do need to know about the history of the periodic table for GCSE, yes. Okay. The second one was John Newland's 1863, the octave rule. Now, this one can be a bit confusing, but effectively he found that when he ordered the elements by atomic weights, just like John Dalton did, because more had been discovered, he found that every 8th element matched with, so every 8 there was a match, or there was similar properties. So for example, he found that hydrogen, 8 elements later, 1, 2, 3, 4, 5, 6, 7, sorry, 8 elements, so the 8th one would be fluorine matched with hydrogen. 8 elements later was chlorine matched with hydrogen fluorine. So he put them in this group because he thought they matched. Again, if we have a look, there are some exceptions to this rule, and actually people have found that it does work only up until calcium. So up until calcium, he had it about right. So hydrogen, fluorine and chlorine were okay. Lithium, sodium, potassium, remember these are all alkali metals, so he did group them correctly. Magnesium, calcium, and he put these all, and up until calcium, he had it right. So every 8 elements he had right, but after that, it goes a bit funny. So for example, in this group, he had iron and oxygen. And we know that iron is a solid, it's a metal, whereas oxygen is a gas. So they are not, should not be in the same group. They don't have the same properties. So that's why, that's the example I've given there. And he didn't leave spaces. So he thought that these were all the elements. So at that point, these were all the elements that had been found or discovered. He thought they were the only elements around, so, and they weren't going to discover anymore, so he put them all into a list. So that's the second one. The third one is the one that's the most similar to our periodic table, which is produced by Dmitry Mendeleev, and this was in 1869. And he also arranged it by atomic mass, the periodic table. Does anyone know what's our current periodic table arranged by? It's not arranged by atomic mass. What's it arranged by? Atomic number, excellent. So he arranged it by atomic mass, but our current periodic table is arranged by atomic number. Well done, everyone, telling me that. But what he did that was better than what the previous periodic table did was that he left gaps. So you can see here is he left this gap, this gap. So he found that he arranged them all by properties, but he left gaps where he thought elements had not been discovered yet. And actually he predicted the properties of those elements, and he was correct. So where he left spaces, for example, here, he predicted what should be there, and he was correct with their properties. So this is the most similar to our periodic table and is the basis of the current modern periodic table. Someone's asking what's the difference between atomic mass and atomic number? Really good question. So atomic mass, or relative atomic mass, is the number of neutrons plus protons, whereas the atomic number is just the number of protons. Okay. Yes, someone's asking, did he switch the places? Exactly, so that's another thing that he did. So if he found that when he was ordering by atomic mass that something didn't quite fit, he would swap the places of them. So for example, he swapped argon, he also swapped the one that someone's just mentioned there. So he swapped the places of iodine over here, and Te, you can see it shouldn't be 128 and 127, it should be the other way around, but because it fit better with the grouping, he did swap them. So what he did was he used the properties, which is how our periodic table is arranged, by properties in groups. So his periodic table was most similar to ours. Okay, so that's a brief run through of the history of the periodic table. Someone's asking me to go back to the John Newland slide. I shall go back there. And are there still more elements to be found? I think most of the elements have now been found, but there's always a chance that some more could be, but most of them have been found. Back then, when these were being discovered, there would be something like 10 every year would be discovered, but nowadays that doesn't happen. It's very rare to find a new element. Okay, so as a very, very brief summary of what we've covered this week before we do some exam questions, let's go through what we've done. So remember, we started off the week by talking about separation of mixtures. So this is just a table of all the different types of separation methods we went through. I've put this table up. I'm not going to go through it. It's just, does anyone have any questions about any of the separation methods that we covered this week? So this is a table that covers pretty much a summary of all the separation techniques. Does anyone have any questions about those separation techniques? Someone's asking me, how do you discover the elements? So a lot of mining took place. Yep, distillation. Okay, so simple distillation and fractional distillation. So remember simple distillation, the example I gave was things like pure water from seawater. So often to produce pure water, we need to boil off that pure water and it goes through a condenser to produce a beaker of pure water from seawater. So the first thing that we'd start off with pure water and seawater is we'd filter. Remember, seawater tends to have sand in it, so we use filtration first to remove the sand. And then we put it into a simple distillation apparatus where we heat a flask of seawater up. And because the pure water has a lower boiling point than seawater, remember seawater's got sand dissolved in it, so the pure water will boil off, all of that water will boil off, and it will go into a condenser. Once it's boiled, it goes into the condenser, it produces a liquid, and it then liquefies and is received in a beaker. So in the original flask where you put the seawater, you'd be left with salt. So remember, seawater has salt and sand in it. You filter off the sand, and you do simple distillation to get just the sand in the flask, and in the beaker that you're left with, you just have pure water. Fractional distillation is about separating miscible liquids, which means they dissolve in one another. So things like ethanol and water and crude oil. Is fractional distillation part of organic chemistry? It is in terms of crude oil and cracking. Yes, someone's asking fractional distillation for crude oil, that's correct. Miscible means that they dissolve in each other. I will go back to the colour slide in just a second. Okay, so if there's no more questions on separating mixtures, oh, this is not what I'm supposed to be. Here we go. So this is now a summary of the halogens, alkali metals, and transition metals that we've covered. Do we need to know about gas chromatography for Edexcel? It's a higher tier topic. It's mainly A level. If they ask you questions, they tend to be application questions. It's not in the AQA syllabus. So this is just a very quick summary of all the halogens, alkali metals, and transition metals. Does anyone have any questions about that before we do some exam questions? How many exam boards are there in science? There's quite a few. So there's AQA, EdXL, OCR, there's the IGCSE exam board. There is one more that I can't remember off the top of my head. Gas chromatography, more accurate than paper chromatography, yes. So gas chromatography separates gases, and it uses a lot more technical equipment than just paper chromatography. Can we go on to exam questions? Yes, sure. Someone's asking me, can transition metals be used as catalysts? Yes, that's one of their many uses. So iron, for example, is used in the Haber process, which is the production of ammonia. What's the difference between OCR and OCR 21st century? Sorry, I don't know the difference between those two exam boards. Alkaline metals. What do we want to know about alkali metals? Someone's just asking me about alkali metals. Why do they have low melting and boiling points? Okay. So remember, we talked about this. It's about the electrostatic attraction between the delocalized electrons and the protons. And it's because there's only one delocalized electron per cation in alkali metals. They only have one electron in their outer shell, which means there's weak electrostatic attractive forces between the cations and the electrons. And that's why the melting and boiling points are low, because only a little bit of energy is needed. Someone's asking me to go back to the properties slide. This is the colored compounds. So I know someone asked me to go back to that. You can't save these slides for future references, but if you go onto YouTube afterwards, this video will be up. And the properties of the metals are here. Colored compounds are the transition metals. They form colored compounds, and it's to do with their electron shells and the losing of electrons. You don't need to know why, but essentially they all form different colored compounds. And these are the ones with blue arrows are the ones that you need to know. And I've done them in the colors that they form. Okay, let's go on to exam questions. Okay, an atom of aluminium has the symbol 2713Al. Give the numbers of protons, neutrons, and electrons. So this is right back to the beginning when we started with our chemistry webinars. Does anyone know then? Okay, good. Protons, 13, excellent. How many electrons then? If there are 13 protons, how many electrons? Excellent, well done. And neutrons, remember, is the atomic mass, so 27 minus 13, which is 14. Well done, everyone. Why is aluminium positioned in group 3? What's the reason for aluminium being in group 3? Great, it has 3 outer electrons. Well done, everyone. Good. Okay, in the periodic table, so this is one of the typical exam questions that you would get now comparing transition metals. In the periodic table, the transition elements and group 1 elements are metals. Some of the properties of true transition metals and 2 group 1 elements are shown in the table below. Use your own knowledge and data in the table above to compare the chemical and physical properties of transition elements and group 1 elements. So this is a 6-mark question, so we need to compare the chemical and physical properties. So remember, chemical properties are things to do with bonding and energy. Physical properties are things to do with kind of hardness. Great, transition metals have a higher boiling point and have more than a 1+ charge. Excellent, well done. That's one of the reasons. Any other differences we can think of? Someone's asking me, why are there 2 ions on the color page? Remember that the transition metals form different ions. Again, it's to do with their electron shell structures. In exam questions, you would be told whether it's a copper 2 ion or a copper 3 ion. Similarly, whether it's an iron 2 ion or an iron 3 ion. Transition metals aren't that reactive. Excellent. Transition metals are normally harder than alkali metals. Excellent. Well done, everyone. Really great answers. Transition metals form colored compounds. Really, really good. Great. So I think we've got some physical and chemical properties there. So yeah, the key thing is that you're making sure you're comparing. So remember, comparing things like saying harder, things that you either have to say the alkali metals have this property, but the transition metals don't, or you have to kind of use a comparative word like harder. I can write an answer. So I'm just going to bullet point the answer so that we can do lots of exam questions. So chemical properties are to do with the bonding. So we can talk about how there is stronger electrostatic attraction in transition metals than alkali metals, which then gives it its property of a high melting and boiling point. Another chemical property is that, a physical property then would be about them being harder than alkali metals. Again, that's to do with the electrostatic attraction. So chemical properties would be that they are less reactive. Again, that's to do with the electrons in the outer shell. You wouldn't need to explain that, but you can say less reactive than alkali metals. Physical property, they form coloured compounds. There you go. So that would be kind of 4 things that you could talk about there. Okay. All right. Okay, transition elements and their compounds have many uses. Iron oxide and cobalt oxide have been added to the glazes on pottery for hundreds of years. So we've not gone over pottery, but does anyone know, why would we add transition metals to pottery? What's special about pottery? Excellent, really good answer. So someone said they are coloured compounds, so are attractive. That's a really good answer, yes. So pottery tends to be attractive, and because they form coloured compounds, that's why they're added to pottery. So it's not about them being unreactive. It's literally about the colours of those compounds. So well done, everyone. So this is a typical question then. We want to work out the formula for iron oxide. So notice how they've told us it's iron 3. So what does that mean? If they've put 3 there, what does that mean the ion of iron forms? So the ion of iron, what does that produce? Fe3+. Excellent. This means Fe3+. Does anyone know oxide? What ion does that form? So that's oxygen. What ion of oxygen is there? Excellent, O2 minus. Okay, so how do we combine those then? So we've got Fe3+ and O2 minus, and we want to form a chemical formula for those. How does that combine? Fe2O3. Excellent, very well done, everyone. So remember, you can either swap the charges, so that would become O3, and that becomes O2. Sorry, just 2, so Fe2O3. Or you can think about it, if iron's got 3 electrons to give and oxygen can only receive 2, the only way that these would work is if iron has 6 electrons to give, so we would need 2 ions, and oxygen has 6 electrons to receive, in which case we would need 3. Okay. Cobalt oxide is reacted with hydrogen to form cobalt. Balance the equation for this reaction. So this is a balancing equation. How do we balance this equation? This is going back to what we did on Monday. What do we need to do to balance this equation? Yeah, we need to balance oxygen. So remember, I always start off by saying what's different. So if we have a look at that first, we can see that cobalt is 3 and cobalt is 3, so they're the same. Oxygen is 4, whereas oxygen over here is only 1. Hydrogen is 2, and if we have a look, hydrogen is 2. So they've actually told us that we're only going to need to balance the hydrogens and the oxygens because they've put the dots in front of those compounds there. So if we have a look then, how do we balance that? Okay, excellent, well done. So if we put a 2 here, we end up with 2 oxygens. And if we put a 2 here, we end up with 4 hydrogens. So someone's saying 2 oxygens. Does that work though? So we end up with 2 oxygens, but if we have a look, there's 4 in cobalt. So that wouldn't work. 4 and 4, excellent, well done. So 4 gives us 8 hydrogens. And if we put a 4 here, we end up with 8 hydrogens and 4 oxygens. So it's 4 and 4. Well done to everyone that tried that. Okay. Cobalt is mixed with other transition metals to make alloys. These alloys are used to make cutting tools which remain sharp at very high temperatures. They can cut through other metals. So cobalt is mixed with other transition metals to make alloys. These alloys are used to make cutting tools which remain sharp at very high temperatures. They can cut through other metals. Suggest 2 properties of transition metals that make them suitable for making cutting tools. What do we think then? They're hard, excellent. That would give you 1 mark for saying they're hard, and high boiling point, excellent. Well done. In this case, I would say high melting point. So remember, transition metals are solids at room temperature. So you want to say high melting point, not boiling point. Great. Malleable would not give you a mark here, because remember that most metals are malleable. They can be changed into different shapes. They're strong, so hard and strong would be 2 separate points. Well done. Great, well done everyone. Okay, let's do a question on the history of the periodic table. In 1866, John Newlands produced an early version of the periodic table. Part of Newlands' periodic table is shown below. Newlands' periodic table arranged all the known elements into columns in order of their atomic weight. So remember, columns just means groups, rows is like periods in the periodic table. Newlands was trying to show a pattern by putting the elements into columns. Iron does not fit the pattern in column 7. Why? Why doesn't iron fit the pattern in column 7? Excellent, iron's a metal. Excellent, because it forms more than 1 charge, whereas the other ones have a -2 charge. Excellent, it's a solid, it's a metal. Really good answers, very well done. In 1869, Dmitry Mendeleev produced his version of the periodic table. Why did he leave gaps for the undiscovered elements in the periodic table? Someone's asking, what are atomic weights? So atomic weights at that point in time had nothing to do with neutrons and protons. It was actually to do with the weight of the elements. So you could add in new ones. Yes, he knew there were going to be more elements. Good. So the other elements would fit the patterns. To fit the patterns he made. Good. Because they didn't fit the pattern, so he left gaps for undiscovered elements. Excellent answers. Well done. Really good answers. So Newlands and Mendeleev placed the elements in order of atomic weight. The modern periodic table places the elements in order of what? Atomic number. Excellent. Well done, everyone. Great. Okay, so we'll stop there just for any Q&A questions. If there aren't any Q&A questions, then we'll go on and do a couple more exam questions.
Thanks, Aman. There have been a ton of questions this lesson, which is great to see. If your question hasn't been answered yet, could you just repeat it in the Q&A, please? I'll quickly answer a couple of online school-related questions before we move on. Will there be GCSE German on the webinars? We don't have plans currently to introduce German, but we are looking at what languages will be most useful and most popular with you guys. So we'll let you know if that is added here and via your email. Someone asked, where is that? How do we use the My Tutor videos and use them effectively? So good question. So on the My Tutor YouTube channel, there will be all of these webinar videos and also some shorter videos from our tutors. So how to use them effectively, I think would be for revision purposes. So as a lot of you are saying, asking tutors to sort of go back to certain slides because you want to copy content down, you can always watch back those tutorials and make notes off that. And also when it comes close to exams, I think there'll be a useful resource hopefully for you guys to just refresh your knowledge again. And the shorter videos, lots of them are tutors just quickly going through some exam questions. So those will be really handy if you want just a few quick practice questions and then to see the method going through those. So hopefully that makes sense. When is next week's plan going to be up? We're working on that for later today, and you'll get an email over the weekend with the schedule. And where do you find the shorter videos? They're also on the My Tutor YouTube channel. I'll see if at the end of this tutorial I can send you all a link in the chat to that, but you can just type in My Tutor in YouTube and all of the videos are just separated into playlists, so it should be quite easy to find. And will there be a biology webinar today? No, there's not biology today. It's just chemistry, English, maths and physics. Looks like not many more content based questions, Aman. So should we do a couple more questions?
Yep, let's go on and do another one.
Brilliant.
Okay, gold is used to make some jewelry. Explain why gold is used to make jewelry. It's shiny, excellent. It's It's not hard. So the person that said it's hard, it's not hard. Gold is actually quite a soft metal. It's unreactive, excellent. So remember, it doesn't react with oxygen, so it doesn't rust or corrode. It's soft, yeah, excellent. All really good answers. It stays shiny, and that's because it's unreactive, so it doesn't react with oxygen. It's easy to mold, really good. It does have a high melting and boiling point, so it's not easy to heat. Someone's asking, why isn't it hard? So it's one of the exceptions to the transition metals that you need to know about. Again, it's to do with its electrons. So just like in Mercury, where the electron shells are arranged slightly differently, and again, it's to do with the electrons in the outer shells, making that metal soft. So there are a lot of metals that have different properties. Most transition metals, or the ones you need to know about, we've gone over today, and they're just specific properties you need to know about. Great, okay, so does anyone know what the purity of gold is? You don't need to know, this is just, yep, 24 karat, that's great, well done everyone. Okay, gold can be alloyed with other metals to produce alloys that have a higher strength than pure gold. Explain why gold alloys are stronger than gold. So this is going back to gold and alloys now. Carat is a way of measuring the purity of gold. So why are gold alloys stronger than gold? So if you can think back to what we covered a couple of weeks ago. Excellent. So someone said there are atoms with different sizes that stop the layers from sliding over each other. That is a really excellent answer. Well done. The layers can't slide over each other in the giant lattice structure. Yep. Different shaped atoms, meaning it's harder to move or shape the alloy compared to the pure gold. Really good. So it's about the ions. So if I draw the electrons or the structure of an alloy, so remember we have, this would be pure gold, all kind of the same size, so the ions can roll over each other, the positive cations can roll over each other, whereas when we use an alloy, there might be bigger particles in there that are going to disrupt those layers and mean that it's a lot harder. What you can see is there's no nice neat layers there, so we can't roll those ions over one another, and that's why alloys tend to be a lot harder. So remember, softness comes down to how easy it is for the metal to roll over one another in the ions, and also to do with the electrostatic attraction. Okay. Oh, we just had a question. Do alloys tend to be cheaper? Yes, because they're not pure metals. So for example, steel will be cheaper than iron because steel contains iron and carbon. So that all tend to be cheaper. So you don't tend to buy pure iron, you tend to buy an alloy. Is the purity of gold always 24 karat? So that is absolute pure gold. So if I go back to that question, so that is the pure gold is 24. So absolute pure gold is 24. Remember, if it's an alloy, it won't be. If there's something else in there, it won't be. So absolute pure gold, yes, is 24 karat. Any more questions on alloys before we move on to another exam question? So I did say that Edexcel exam board do need to know about alloys. The AQA exam board do too, but what is 100 karat? So I don't know what is 100 karat. That's just a number for purity. Again, gold is always 24 karat. So it's a way of measuring purity. So I'm not sure what is 100 karat there. Again, it's just an answer. Okay, so we'll do another exam question. So in 1869, Dmitry Mendeleev produced his periodic table of the elements. What evidence did Mendeleev use to decide that alkali metals should be in the same group? Someone's asking me, how is white gold different to yellow gold? It's to do with the color that it produces. So white gold tends to be a white color, whereas yellow gold will be gold, the gold color that you expect. Reactivity, their properties. Someone's saying, I don't understand alloys. Would you mind telling me specifically what it is you don't understand, or is it just alloys in general? So everyone that's saying their properties and their reactivity, you're exactly correct. So Mendeleev looked at the properties of alkali metals, saw that they had the same properties, so put them in the same group. Well done. So the person that's asking me about alloys, let's go back to that. Okay. So an alloy means that instead of having a pure metal, you will have some kind of other element in there. Alloys are always formed from one metal and some other element. So for example, if gold had some other element in there, we know that steel is made of iron and carbon. And so what happens is, instead of having a nice complete regular structure like here, you end up with different sized particles or atoms. So remember, not every atom is the same size. So if we disrupt our pure metal with some other element, so for example, if we disrupt our gold with some other element, they could be bigger or they could be smaller. And that means that these layers cannot slide over one another. So remember, these are cations, positive ions, and they can't slide over one another if they're not in a regular structure. So alloys tend to be harder because the layers cannot slide over one another. Someone's saying, can gold only be created through a supernova? I'm not sure the answer to that question, sorry. Can some people be allergic to gold? Yes, although it's very rare. More people tend to be allergic to things like steel, because remember I said that, so a lot of jewelry can be made from things like stainless steel and things, and that can react with the skin. So jewelry that's not made from sterling silver, for example, can be reactive, and that's because it reacts with the oxygen in the air, and therefore can react with your skin as well. Okay, describe how the elements in the modern periodic table are arranged in terms of protons. So how are elements in the modern periodic table arranged? Titanium does not react. That's why often it's used in hip replacements. It's a very non-reactive metal. So from ascending order in terms of protons. So yeah, in terms of protons, they're all done in atomic number. Well done. In terms of electrons, how are they arranged in terms of electrons? Groups, yes, it's to do with the outer shell. Well done. So I said titanium doesn't rust. Why is titanium used for jewelry? Again, because it doesn't rust, doesn't react. Same like gold doesn't tend to react, and sterling silver doesn't tend to react. That's why a lot of jewelry is made from that. Okay, well done everyone. State 2 properties of transition metals that make them more useful than alkali metals for making water pipes. This will be our last exam question then. State 2 properties of transition metals that make them more useful than alkali metals for making water pipes. Stronger, excellent, that would get you 1 mark. Harder, that would also get you another mark. Alkali metals do react with water, so exactly, they're not, yep, they're unreactive. Good. Stronger and harder, high boiling points. Again, I would avoid using boiling points, it'd be melting points. So remember, the metals are solids at room temperature, so I would say high melting points. Boiling point means liquid to gas, whereas metals are solids in the first place. Less reactive and hard. Excellent, really good answers, everyone. Okay, so before we finish, any questions, any last questions?
Do you have any recommendations, Aman, for any GCSE chemistry websites to help with revision?
So I use things like Physics and Maths Tutor. There's also BBC Bite Size is really good. It tends to use the syllabus and the specification for every exam board and pretty much writes down everything you need to know. The only thing BBC Bite Size doesn't tend to do is have very good exam questions, but the content they have is really good. So I would recommend BBC Bite Size. There's also something called Chem Tutor online. They tend to have quite detailed notes. So any of those websites.
Great. And do you have any tips for remembering chemical equations?
So I don't tend to remember chemical equations. I tend to remember what types of reactions can occur. So for example, yesterday we looked at the alkali metals and how they can react with oxygen, how they react with water, and also today we looked at some of the reactions. So I remember the reactions that can take place. So I remember, for example, when an alkali metal reacts with water, it produces hydrogen and hydroxide gas, and a metal hydroxide. And the hydrogen's the gas, the metal hydroxide tends to float on the water before dissolving. And I think watching videos can be really helpful. So I showed a video yesterday of potassium reacting with water. And ever since I watched one of those videos, I kind of remember the reaction of alkali metals with water. So I think kind of learn the reactions that take place rather than the equations, if that makes sense.
Thank you. And had a question which was, will we be doing GCSE Classics? It's unlikely that we'll be doing it anytime soon, just because we're starting with the subjects that the majority of students are studying, but potentially if we're expanding out into lots of other subjects. So probably not over the next few weeks is the answer to that. And when will A-level sessions start? We're not 100% sure at the moment. We're still figuring out the timings of that one, so just watch this space for that. And that's the same for Key Stage 3 as well. And are there going to be Key Stage 2? We don't have plans for Key Stage 2 at the moment, but if that is something that we introduce in the future, we'll let everyone know via email. So as it's 11:15, I think we'll wrap up there. Thanks for attending today. Great to see lots of you in the session, and hopefully see lots of you in further sessions later today, or if not, back next week for our next GCSE Chemistry session. And thank you very much, Aman, for today's session.
Thanks, everyone. Bye.
Thanks, everyone. See you later.